Hello and welcome back. So last time we began looking at the method to test a hypothesis, a claim about a parameter of a population. So the first step was to identify the claim and then to give it a symbolic form, meaning we write it down with more mathematical notation. And then we want to identify the null hypothesis and the alternative hypothesis. So to reiterate, the null hypothesis is going to say the parameter is equal to something, and the alternative hypothesis is going to say that the parameter is either greater than or less than or not equal to the value. And we want the alternative hypothesis to be the claim that we think is true. We select the significance level, which is the probability that we make an error. So we want a small probability that we make an error, so we want a small significance level. What we have left to do is to discuss the test statistic and then finding either the p-values or the critical values, which allow us to make a statement either in favor of or against our hypotheses. So let's look at our test statistics. So when we are looking at test statistics, we could be looking at different things. So for instance, we could be looking at proportions, we could be looking at means, or we could be looking at standard deviations or variances. And each one comes with a different test statistic. So let's look at proportions first. So we normally denote proportion with p. And when we look at sample proportions, provided that these conditions are met, as in we have at least 5 successes and at least 5 failures, the sample proportions we get are normally distributed. And the normal distribution from which they come is right here. So this is our test statistic. And you will recognize this from the construction of confidence intervals. So when we construct confidence intervals, we used this test statistic. When we are looking at means, on the other hand, if we do not know the population standard deviation, our mean is going to come from the t distribution. So this was the student t distribution, because we can't assume that it formed the normal distribution. It's slightly off, so we have to use the t statistic. Whereas if we know what the population standard deviation is, we can use the normal distribution, and everything will be normally distributed. Now, both of these also require that our population be normally distributed, or we have a sample of at least 30, at least 30. So the last ones are standard deviations and variances, and this was the one that we looked at the chi-squared distribution that looks something like this, where it was not a normal distribution. It had a right tail, but in order to even use the chi-squared distribution, the population had to be normally distributed, and chi-squared was this. So in each of these, we can calculate the test statistic, and roughly what the test statistic tells us is how unusual was our sample. If our sample was really unusual, we will be able to reject the hypothesis. We'll be able to reject our claim, because unusual things shouldn't happen very often. So we get to reject any assumptions that we made. For our example that we've been looking at in the last video, this is a proportion, so we will use the test statistic from Z. So from our example, we asked 1,009 people whether or not they would be comfortable or uncomfortable with drones making deliveries, and we found that 54% of our sample was uncomfortable with it, and we are testing whether or not at least 50% of the population would be comfortable, would be uncomfortable with drone deliveries. So here we have p hat is our sample statistic, because it's 54% of our sample was uncomfortable, and we are testing the population being 50% of people would be uncomfortable with this. So our test statistic, because we're looking at proportions, is going to be z. Everything is normally distributed. And if we plug these in, we'll have 0.54 minus 0.5 by the square root. P here is 0.5. Q is the complement of this probability, and if 50% of people are uncomfortable, then 50% of people would be comfortable. Divide by n, which is the size of our sample, and we get 2.54. So this is our test statistic. And what this refers to is in the standard normal distribution, so say with a mean of 0 and a standard deviation of 1. The question is this unusual, or is it not unusual? So in order to determine whether or not this is a reasonable test statistic, we have to define what's called the critical region. And maybe a more enlightening term for this would be called the rejection region. So this is the area corresponding to values so extreme we would reject the null hypothesis. This would be corresponding to values that are so extreme we would think that they're very unusual, and we could reject the assumptions that we made in making the graph. So for instance, if our if our alternative hypothesis was that that proportions were greater than some value, our rejection region would be to the right, meaning that when we look at our null hypothesis is always going to be p is going to be equal to something. Well, if we have values that are so extreme that they're way over here, our null hypothesis we would reject. So this right here is going to be the critical region. Furthermore, we could be in a case where our null hypothesis is going to be p is going to be less than something. So again, if we're looking at this is our alternative hypothesis, excuse me. So our null hypothesis is that p is equal to something. Our alternative hypothesis is that p is either going to be greater than, less than, or not equal to something. In the case when we're less than, our critical region is going to be to the left. Critical region. So depending on whether or not we're looking at a null hypothesis where the alternative hypothesis is that something is too big or something is too small, it will depend. The critical region will be on either side. Likewise, if the alternative hypothesis is simply that p is not equal to something, and we haven't specified whether it's bigger than something or smaller than something, we will have a critical region with two tails. So both of these are going to be critical regions. And alpha was our significance level. And alpha is going to be the area of this guy here. Alpha is going to be the area of this guy here. And alpha is going to be the area of this and the area of this guy. So, excuse me, we split alpha apart across both of them. So it'll be alpha over 2 and alpha over 2. That's my mistake. So, so ultimately, we can figure out whether or not our test statistic is unusual in two ways. We can either see if our test statistic lies in the critical region, in which case we reject the null hypothesis if it's in the rejection region, or if it's not, then we can't really say much. So there are two ways to do this, and the first way that we'll look at are what are called p-values. And the p-value is the probability of getting the test statistic as extreme as the one from the sample. So, for instance, in our example, our test statistic was 2.54. Is that unusual? Is that quite probable? What's the probability of getting 2.54 as a test statistic? In order to calculate this, the p-value is going to be the area to the left of the test statistic. If we're looking at a left tail, it's going to be the area to the right of the test statistic. If we're looking at a right tail, and it's going to be twice the area beyond the test statistic if we're in a region with two tails. So again, let's look at our example. So our alternative hypothesis is that p is greater than 0.5. So our normal distribution looks like this. It's not very well drawn, but oh well. And we're looking at whether or not p is going to be greater than 0.05. So we are looking at a right tail. Furthermore, in a standard normal distribution, our test statistic, 2.54, is going to be right here. So the question is, what is the area there? So to do this, we'll just come over to StatCrunch. If we go into statistics calculators, and we are using a normal distribution with the proportions, and we want a right tail, and we want this to be greater than 2.54. And we find that the area to the right of a test statistic of 2.54 is 0.0055. So the p-value here is 0.0055. And just as a little warning, we're talking about p-values, but we also use p to represent the proportion of the population, and p hat to represent the sample proportion. There's lots of p's floating around, so just be careful that you know which one's which. So the question is, what do I do with my p-value? The probability of getting this test statistic, or a more extreme test statistic, is 0.005. That's quite low. If the p-value is smaller than our significance level, we get to reject H0. The result was so unusual that something fishy was going on, so we get to conclude that H0 is false. If the p-value is greater than alpha, we can't say much. The result could have happened by chance, but it wasn't so unusual that we couldn't say so. This is calculating the p-value. The other way to do this is to just look at the critical regions. And so for instance, if we're looking at p-values that are, if our alternative hypothesis is looking at p-values greater than something, again we have a right tail. And there are two situations. Either the test statistic is contained in the rejection region, or the test statistic is not, and it'll be somewhere else. So if it's in the rejection region, we reject our null hypothesis.